general relativity, step by step. Last time I used the Lorentz transforms to transform a contravariant vector. I'm just going to quickly go through what happens when you have a covariant vector. Let me just write the rule down, certainly for these two-dimensional things here. We've got V, let me just zoom in a little bit. We've got V alpha bar equals dx V, oops, I don't know why it does that, beta. That beta is going to contract on that. That's no bar, there's no bar there. There's a bar there, so there's a bar there. Bar alpha, bar alpha. So V bar 0, for example, equals dx 0 by dx bar 0 V0 plus, now I'm going to put beta equals 1, dx 1 by dx something V1. And the something is going to be a 0, isn't it? And that's a bar. Now, in order to do this, we need to invert this. Relationship here. So we need to take a matrix inverse of this matrix here, because I want x0 equals something in terms of x bar 0s and x bar 1s. So I need to take a matrix inverse of this guy here. And I think I showed, it's an exercise I guess for the reader, that gamma beta to the minus 1 matrix inverse equals gamma minus gamma beta minus gamma beta gamma. That's obvious on physical grounds because beta has been replaced with minus beta. Of course that doesn't change gamma at all because it's a function of beta squared. So now I can talk about x0 equals, just from this one, gamma x bar 0 minus gamma beta x bar 1 from the top row of here, and x1 equals minus gamma beta x 0 plus gamma x bar 1. Yeah, that's obvious on physical grounds, but now it's mathematically rigorous as well. There we go. So I can say that V bar 0 equals, just copying this formula here, dx 0 dx bar 0 is just going to be gamma, keeps on moving, gamma V0 plus dx 1 by dx bar 0, which is minus this term here, gamma beta V1. And of course with an analogous expression, well I may as well just write it down. That's going to be the second row, minus gamma beta V0 plus gamma V1. So there's the rule for transforming a covariant vector according to the Lorentz transforms which we've so painstakingly built up. What I'm going to do now is to show you some examples of sensible covariant and sensible contravariant vectors that have got physical meaning. The reason this is hard, or one of the reasons this is hard, is that we're trying to combine physics with the mathematics. I think the mathematics is relatively straightforward, and the physics, I dare say, is relatively straightforward. However, bringing the two together is quite difficult, and this was Albert Einstein's genius, or one aspect of his genius, that he could bring the mathematics and physics together in a way that made sense to both the mathematicians and the physicists. Quite a profound level of genius there. I'm going to stop there. Stop.